Now, our goal is to take this idea of the planetary model and then bridge into this quanta or this quantum model of the atom, okay? Let's take it to the next level. Let's get past middle school science and let's talk about what is our newest and our best model of the atom, and can we even visualize it? So that's kind of where we're heading with this. But before we get there, we gotta learn a few things, okay? So the first thing is how do we know the electrons are at set quanta? Okay, so how do we know this? What experimental information has given us this idea? Okay, well, it comes from light signatures. And you guys, if you had Earth Science at Egan High School, you learned this in Earth Science. You guys got out spectroscopes, the little triangular black things, and you had to stare at what looked like tiny little neon lights. And I think you even did a lab where you had to draw the lines and measure them and label this and that kind of stuff. We're not going to do that. We wouldn't do it in a normal year. But this data is what actually determined that we had quantized energy, because there's dark spots. So we have these really bright line spectrums. Okay. Now, a little background. When it comes to light, light is energy. Energy comes in packets called photons. Okay. And if you have a really bright beam of light in this particular energy, this particular color, that means that there is electrons that can reside at that energy level, okay? Now, we don't ever see for helium anything here or here or here or between here, which means the electrons can only be at certain amounts of energy, all right? Now, how does that work? Well, these are called atomic emission spectrums, all right? We already talked about them being their own signature. Those lines indicate that specific quanta. Here's the trick, though. So where do the lines come from? So here's where the lines kind of come from. When you excite electrons, so if you give electrons extra energy, like we do when we use neon lights or these kind of things, or when you put energy into distant stars, those kind of things, what happens is you excite those atoms. Those atoms get extra energy. That extra energy then gets put into those electrons. So the electrons are given boosts of energy. Well, just like people, you give them a whole bunch of sugar, you get a boost of energy, you start jumping up, okay? So what happens is those electrons literally will jump to the next energy level, all right? When that happens, they get excited, okay? But they're not stable at the next energy level. So here's your electron, right? Hanging out, it's stable, it's called being on its ground state. Fine. If I give it some extra energy, so you're going to see kind of a bolt of energy come in here and nail this thing. So when that happens, energy comes in, it jumps to the next energy level. When that electron jumps up here, it is not happy. It does not like to be at the second energy level, okay? It belongs on the first. So what happens to that electron is it will fall right back down, okay? You can give it more energy and make it jump higher. You can give it more energy and make it even jump higher. Every time you make a jump, it absorbs more and more energy. It's moving faster. It's further away from the nucleus. Now, these are all unstable locations for that electron. Okay? They're called being in the excited state. Electrons don't last in the excited state. As soon as you excite them, then they actually instantaneously dump that energy back out. So as soon as this electron jumps up, now, obviously because I'm talking, we're letting it hang out here at the top here. But in real life, it never stays there. It instantly falls back down. So when it falls down, okay, what happens is it drops down. Now, we don't see anything happening here. The reason being is that depending on the atoms you have, these energy levels are in different locations. So if I place this more realistic of an atom that we experience, okay, and I make it jump up, and then I have it fall back down. What happens when it falls down, it releases energy. That energy it releases can be tracked by an emission spectrum over here. If it falls down again, it falls a different distance, so it releases a different amount of energy, okay? If it falls again, it releases a different amount of energy. So if this was a particular atom, it could fall this far, or this far. Each fall represents a very specific amount of energy, or a quanta of energy, which means it creates 3 different signature lines, okay? Now, a different atom. We just change this a little bit. Don't need to change it very much because these are pretty touchy. If we jump it all the way to the top, and then and I reset this, and it falls, it's going to create 3 different lines, okay? If our atoms only had 4 energy levels, we would only see 3 lines all the time. The reality is we see lots more than that, okay? So if we move over here, what we're seeing here is running off the projector of the iPad. So over here now, okay, we have a device that is pushing out excited light from these spectral tubes. Very much like you guys did in your 9th grade Earth Science class. It's just a little bit different stuff that I have, okay? This particular element, okay, we're running this, actually collecting data on this right here. It's the wavelength and the intensity that it's reading, these different wavelengths, has spikes in 3 different locations. So this particular element has 3 different places. Here's a 4th one. Here's some other smaller ones you see, that it is jumping these electrons up and falling back down, okay? If I change this to a different element, I've got to warm up for a second. It'll turn on for me. Wait for it. Okay. Now we change to a different element, and you see that we see a different signature. So there's a different amount of spikes. So this element has lots of different levels it can jump and fall down on. So you see there's one here, 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 several through here, bunch through here. This element probably has a lot more electrons because they can make a lot more different falls, okay? You emit light when you fall back down and release energy. When you absorb energy, you jump up and nothing visual. It has to be the falling down. We change it again to another element, okay? This one's got all kinds more different ones, but this is a different signature, okay? Change it to another one. And once again, we get a whole new signature, okay? So each element has its own set energy levels, which creates its own signature, okay? Now, astronomers have used this to be able to map out the gases in different stars because they create their own signatures. And if we can track that light coming to our planet, we know what gases are being burned off in those stars, which is pretty cool that we can do that, okay? It comes down to this idea of what these emission spectrums that we see happening, right, inside of our system. Now, because of this, we know that electrons have to have set quanta of energy, all right? Because they emit light in very distinct lines or very distinct amounts of energy, okay, which we call photons, all right? So that's our first piece. We know that electrons can only be at very set energy levels or quanta of energy. That's in the planetary model. Now, that's one piece of the puzzle.